Hi everybody, welcome to Test 3 review in Calculus 2. As always, we have the topics of the question on the top, but this time we have the formula at the bottom of the screen. Right, let's start. First we have the limit of sequence. So limit of sequence is just the limit of this term, and just like the limit of a function when n goes to infinity. So the first one. So we just take limit when n goes to infinity of that term, which is a plus 9n over 3 plus 2n. Now what we have here is a polynomial over another polynomial, and here's another note. For a polynomial, as n goes to infinity, only the highest power term matters. Let me write that out. As n goes to infinity, only the highest power term matters, and this is for polynomial like that. It works for polynomial. So in this case, we will only take the highest power term here and here, and we say that when n goes to infinity, we only have 9n over 2n, and n cancel out. This is just equal to 9/2. Of course, that's just 9 over 2. That n cancel out. Right, so that's the first one. Pretty straightforward. Right, next one we do the same thing. We take the limit, find the limit as n goes to infinity. We have -1. Let's just write that again. -1 to the n power 1 minus 5 to the n. Right. Now, since n goes to infinity, n 5 over n, this term will go to 0. We have a finite number divided by infinity, so that's going to be 0. So this will go to 0. This is still 1, and the -1 here will just negative or positive. So because this one goes to 0 as n goes to infinity, we have 1 minus 0, so this will be equal to 1, and we just have -1 to the n power. So pretty much the limit equal to -1 to the n power times 1. So this either 1 or -1 depends on n is odd or n is even. So if it is even, then the limit equal to 1, and if it is odd, it is equal to -1. Because those values are not the same, this one is divergent. The limit is divergent. Right, let me. So, and that is that. Right. Next, we have the limit of this. We do the same thing. Find the limit of this sequence. So what we have, we still take limit as n goes to infinity of sine of n over n squared. Right. Remember, the limit of the sequence is just like the limit of function. Even though the sequence it might not be continuous as a function, but the limit we find the same way. Right. So we notice that we have sign of a number. So sign of anything is between -1 and 1. That's where we start with. We have sign of n is between -1 and 1, regardless of the values of n. Now, if we divide by n squared on both sides, by both sides I mean everywhere, what we have here is -1 over n squared. We divide by n squared is positive because n go to infinity. So we don't have to reverse the inequality. If we divide by negative number, we have to reverse it, but not on this one. Now notice that as n goes to infinity, this go to 0, this go to 0. So we say this one goes to 0 and this one goes to 0 as n goes to infinity. Since the left bound and the right bound goes to 0, it forces the middle has to go to 0 as well. That is the Swiss theorem. So because of that reason, limit of psi n over n squared is equal to 0. That is by the Swiss theorem. Right, so let me update that list. Next we'll go to geometric series. Now the first three questions is about sequence, meaning a particular term in a sequence. The series is where we add all of those terms in the sequence. So we have the sum like 4 and 5 here. Right. So for geometric series, the formula at the bottom. So this is the infinite geometric series. Alright, I write what we need here. So the sum of geometric series, I just say the sum is S, is equal to the first term over 1 minus R. A is the first term, R is the common ratio, but only when R is between -1 and 1. Here we have under the convergence, R is absolute values of R less than 1. Equivalently, we can say R is between 1 and -1. If it is greater than or equal to 1 or less than or equal to -1, it will be divergent. Right, so this is what we have. Now, let's look at this one. In this series, the first term is 1. And the common ratio. To get the common ratio, what we do is we find a number that where we multiply 2, we get from this term to the next. So from 1 we multiply by -7, we get to the next, multiply by -7, we get to the next number, so by -7. So R is -7. And here we see that -7 is not between -1 and 1. So this is divergent. The series is divergent. From -1 to 1, the series is divergent. Or just say the series diverges. Right. It has to satisfy this condition. Right. Next, we still find the sum of the geometric series here. By the way, the sum of the formula is at the bottom right hand corner of the screen. So we have that. So first, we find the first term. If we just want to write a few terms out, we're going to put 1 here. We have 4/7 is the first term. The next term is 4/7 square, which is 4/49. Right. And then so on. So actually I will rewrite the sequence as follows. I mean the series as follows. Put the 4 here and 1/7 to the n power. And after that, I can put all of the 1 and 7. When it is written like this, we can see that the common ratio is 1/7. Another way to check is from this term to this term, we have to multiply by 1/7 to get from this term to the next. So we have the first term is 4/7 and the common ratio is 1/7, and that's what we have. Now r is 1/7 and we have 1/7 is between -1 and 1. So that one is good. That condition is good. So the sum is equal to the first term over 1 minus r. The first term is 4/7. This is not 4. The first term is where we have the bottom limits. Bottom limit is substituted into the formula, and we have that term, which is 4/7. So 4/7 over 1 minus 1/7. Right. I will multiply top and bottom by 7 to eliminate the denominator. So that gives us 4 on the top, 7 minus 1 at the bottom. So we have 4/6, which is 2/3. Right. So that's what we have. So geometric series, infinite geometric series, the sum is given by the first term over 1 minus the common ratio, but the common ratio has to be between -1 and 1, otherwise it will be divergent. Right, so that's what we have. Next, we go to the telescoping series. This review and this test, we have a little more question, but each question doesn't take a lot of time or space to do. This one though, you might want to write a little bit smaller because it might take little space. All right. So first, it is given as a fraction like this. First thing, I try to do the partial fraction. So 4/n times n plus 3. The partial fraction, we have a/n plus b/n plus 3. The least common denominator is n and n plus 3. Multiply both sides by that. We should have 4 equal to a times n plus 3 plus b times n. Multiply it out. an plus 3a plus bn combine like terms, these two terms have n in it. So factor out an n. We have this. And then 3a is a constant by itself. So that's what we have. When we look at this, we match the coefficient. We have no n on this side. So we're going to have a plus b is equal to 0 and 3a is equal to 4. We don't need the calculator here, because here we can say a is equal to 4 over 3. If a is equal to 4 over 3, we put it back into a here. So we have 4 over 3 plus b is 0. So b is negative 4 over 3. Right. So when we have a and b, we can decompose this equal to, I just say 4/3 and plus 4/3 negative 4 over 3 and plus 3, and that is the partial fraction. Right, now we're going to write that sum, write out a few terms, and then we will see what this is about. So instead of write that term, I'm going to use this instead. So it's just say 4 over 3. That's alright, let's just write 4 over 3 over n like that. We don't need to write 4 over 3n. That's alright. Right. Now first, when n equal to 1, I'm going to put 1 in here, and we'll just write that over 1. And then let's write the minus. I'm going to put minus there. 4 over 3, n equal to 1, so that will be over 4. So that is when n equal to 1. Now when n equal to 2, we're going to have 4 over 3 over 2 minus 4 over 3. 2 plus 3 will be 5. There will be more. 4 over 3. Now n equal to 3. Over 3. 3 plus 3 going to be 6. Just write one more. 4 over 3 over 4 minus 4 over 3 over 7. We're in our space, but that's all we need. So when we look at this, we see that focus on this term with the negative sign and this term with the positive sign. As you see, this is called a telescoping series, because ultimately this term will cancel with something. We have a positive and a negative that will cancel out. What remains, the terms that remain will be this one, and this one. Everything else will cancel out. Those two cancel out. This one will cancel with the next, and then so forth. So what's left here is 4 over 3 over 1, just 4 over 3. 4 over 3 divided by 2, so that's like 4 over 6. and then 4 over 3 is 4 over 9. Yeah. So everything else cancel out except this term will remain, this term will remain, and this term will remain. Every negative term we cancel with one of the positive term on this side, and we just add all of them up. So common denominator is 18, and so multiply by 6, 24, by 4, 16, that's 40, and then 2, 8, 48 over 18, 48 will be 24 over 9. Sorry. Yeah, just this multiplied by 3, so this will be 12. Yeah. So that is 44 over 18, which is 22 over 9. Yeah. So those three terms remain. Everything else cancel out. So that's what we have. So that is typical telescoping series. Divergent test. Right. Divergent test. Just by the name of it, it only works for divergence. Let me roll down. So divergent test. So let's look at the table, the head of row. So here we have convergent and divergence. For divergent test, we cannot use that for convergence. But if the n term is not 0, it will be divergent. So what we do is we just find the limit when n, in this case k goes to 0. So we said if the limit, this is the divergent test, if the limit at n goes to infinity, the n term is not 0, it is divergent. That's all we can say about it. If it is equal to 0, it will be inconclusive. We cannot say it is convergent using this test. So we'll check the limit as k goes to infinity of k cubed over e to the k. Now, obviously, when we put infinity in here, we have infinity cubed, infinity over infinity. So let's just write that real quick. What we have here is infinity over infinity, which allows us to use the Hospital rule. Which we take derivative of the top and derivative at the bottom with respect to k, so the same thing. Right, same thing, infinity over infinity, so we use the Hospital rule one more time. Give us 6k over e to the k, and that's still the Hospital rule because we still have infinity over infinity. Oh, sorry. Limit k goes to infinity of 6 over e to the k. Now when k goes to infinity, we have a 6 over e to infinity because that one goes to 0. We have a finite number divided by infinity, so that 0. So if it is 0, the test is inconclusive. We don't have that for convergent. I mean for divergent. So inconclusive. Yeah. Right. Next we have the integral test. So let's look at the integral test. So this is the integral test. it says that the integral and the sum both will converge or both will diverge, but the values are not the same. We can, if the integral converges, so does the sum. If the integral diverges, so does the series. But the function have to be continuous, positive, and decreasing. Right. So this one obviously decreasing because we have the same number on the top. The denominator is getting bigger and bigger. Eventually go to this go to 0, which is good. And it's positive because of the square root. It is decreasing and obviously continuous too. So that's one good. We can use the integral test. I'm not going to do this one. I'm going to do this one instead. So first, we usually if we have the integral, we don't want to use n here because n is an integer. So we're going to use x instead. So first, we're going to let a function be cosine of 1 over x squared. Now we will find the limits, the integral from 1 to infinity of the function. Notice because of the infinity here, it is an improper integral. So first I will replace this limit. The upper bound by the, just say b goes to infinity. Now that integral will go from 1 to b. And we have cosine of 1 over x squared dx. Right. This is a substitution problem. It will let u equal 1 over x, which is x to the negative 1. We can take the derivative. Du is equal to negative x to the negative 2 dx. Now we bring the negative to the other side. X negative 2 multiplied by x squared on both sides, if you will. So what I do here, I just multiply both sides by negative x squared. X squared and x to negative 2 cancel out, negative and negative cancel out. So basically we just have dx equal to negative x squared du, and that is the substitution. I hope we have enough space here. As far as the limit goes, when u is 1 over x, just use different colors here. When x equal to b, u is 1 over b. When x equal to 1, u is equal to 1 over 1, which is still 1. So what we have here is cosine of u still over x squared though. But we have negative x squared du for dx. So substitute in for this dx by negative x squared du. The x squared cancel out. We still have the negative sign. We'll take our sign of the integral. So we have limit b goes to infinity. We just have cosine of u. Integral of cosine is sine. So we have negative limit b goes to infinity sine of, sorry, kind of run out of space here. Integral of cosine is just sine, and we go from 1 to 1 over b. So that is negative limit when b goes to infinity. Now we have sine of 1 over b minus sine of 1. Now 1 over b, since b goes to infinity, 1 over b go to 0, and sine of 0 goes to 0. So pretty much we have 0 here, and we have negative sine of 1. So this is just equal to sine of 1. Which is a finite number. So this one is convergent. Sorry, I didn't leave enough space there. Right. So if it is convergent, then the series is convergent as well. But that is the sum of the series is not the integral. So as long as the integral equal to a finite number, it is convergent. Right. Next, the P series. Even though it did not say anything, this is a P series. And the P series is given in that form, so I will rewrite that. So we have, actually we can put the factor the 3 outside of the sum. So we still just have 1 on the top, and then the k to the negative 1 over 7 move down to 1 over 7. Actually, let's just do this first. So this is the P series where P is equal to 1 over 7. And for the P series, if it is less than 1, P less than 1, it is convergent. I'm sorry, it should be the other way around. P less than or equal to 1 is divergent. P greater than 1 will be convergent. Since this is P equal to 1 over 7, which is less than 1, so this is what? So this should be divergent. Right. That's P series. Number 10. Next we go to something very rather important, the ratio test. Right. So the ratio test, pretty much this is the ratio. We take the ratio of the next term divided by this term. If the limit less than 1, then that is convergent. If it's greater than 1, divergent. Equal to 1, inconclusive. You can see the formula there. Of course, all the terms are positive. Usually we use the ratio test when we have factorial or powers, something like this. So first we'll take the ratio of the next term over this term at n goes to infinity. So when n at a sub n plus 1, we're going to put n plus 1 top and bottom here. So we have 4 to the n plus 1 and n plus 1 factorial. That is factorial. The bottom we have just a sub n, which is 4 to the n over n factorial. Multiply reciprocal. We have 4 of n plus 1 factorial, and then multiply the reciprocal, we have n factorial over 4 to the n. Right. 4 to the n plus 1 we can say is 4 times 4 to the n power. And n plus 1 factorial we can write as n plus 1 times n factorial. And then we have n factorial 4 to the n. Here we can simplify 4 to the n and n factorial. So we have 4 over n plus 1. So this, we have the limit of just 4 over n plus 1. When n plus 1 at the bottom, when n goes to infinity, we have 4 over infinity, which goes to 0. A finite number divided by infinity, so that is 0. Now if it is 0, which is less than 1, which is convergent. Right. Next one, we do the same thing. Find the ratio of n plus 1 over a sub n. So the next term divided by this term as n goes to infinity. Right. We're going to put n plus 1 into n. So we have n plus 1 to the 7 over 7 to the n plus 1. I wrote that wrong, okay. And then we divide by a sub n. We can just say we're going to divide a sub n, which is, notice I'm write the division sign here instead of write the big fraction like that. Right, which the same, right? N over 7 to the n. You can write like this or like that, it doesn't matter. Now divide by fraction is multiply reciprocal. So 7 to the n on the top and to the 7 at the bottom. Now we rewrite a little bit. N plus 1 to the 7. Cannot do anything with that, so I'm just going to leave that there. But this one we can say 7 times 7 to the n, and then 7 to the n, and then n to the 7 power. Right, what we can simplify is 7 to the n power. Cancel those out. So if n goes to infinity, n plus 1 to the 7. At the bottom we have 7 n to the 7 power. Right. Now, did we refer back to the first question? We say that if it is a polynomial at n goes to infinity, only the highest power term matters. So we can just pretty much drop the plus 1 here, because if n goes to infinity to the 7, if with plus 1 we raise to the 7 power, it's still infinity, that is. So by that process, n will be a lot bigger than 1 when n goes to infinity. So plus 1 or not doesn't really matter. Or we can say between those two, this one has the higher power when n goes to infinity. This is the only term that matters. We cancel this out. It is 1 over 7. So the ratio is 1 over 7, which is less than 1, which is convergent as well. Right. If we have something bigger than 1, it will be divergent. If it is equal to 1, it will be inclusive. The terms should be positive before we do anything. Right. So that is the ratio test. Right. Let's update the list first. Right. There. We did the P series. Next, the root test. The root test are useful when we have anything raised to the n power like this. We know that we're going to take the n root, because the n root will cancel with that power. Alright, what the n root says. The n root says that if when we take the n root, and if it is less than 1 as n goes to infinity, then it is convergent. It will be divergent. If it is bigger than 1 and equal to 1, it will be inconclusive. So first, let's just say if we take the limit when n goes to infinity, we take the n root of this term. N root cancel with n. The reason we can do that, even though we might have a situation of technically when we have the square, it's just absolute values of a. It's not a, but notice that ln of n is positive when n bigger than 1, and so pretty much we have positive on the top, positive on the bottom, and which is positive. Remember, the root test only works if the term is greater than or equal to 0, and all the terms are greater than or equal to 0. So it is good. We can use the ratio test, and because it is greater than or equal to 0, the root and the power cancel out. Otherwise, we require the absolute values when the power is even. So there's a lot of things here if the term is negative. We cannot do that. Anyway, since the power and the root cancel out, we just have 3n minus 8 here. Right, when we put infinity in here, ln of infinity, 3 times infinity minus 8, infinity over infinity, that is indeterminate. So we use the Hospital rule. So use the Hospital rule. Derivative of ln of n is 1 over n. Derivative of 3n minus 8 is 3. So we will have 1 over n divided by 3 is like multiplied by 1/3. So have 1 over n multiplied by 1 over 3. So we just have at n goes to infinity, 1 on the top, infinity at the bottom, so it will be 0. A finite number divided by infinity is 0. So because it is equal to 0, which is less than 1, which means the ratio test, the root test, tells us the series is convergent if it is less than 1 here. So convergent. Right. Next we have the comparison test. So we're going to compare this to some series. Right. So first, comparison test, or usually somebody prefer this to direct comparison test. So what we compare to, oops, sorry, should not do that. So we're going to compare if we have something that is less than convergent, less than the convergent series, it will be convergent. If we have something that is greater than a divergence, it will be divergent. So less than convergent is convergent, greater than divergent is divergent. Right. So first, when we look at this, again, remember this kind of, let's just put this as a rational power. N to the 1/2 and 9n to the 1/3. Right. Kind of like polynomial here, the highest power matters. So we just take the highest power. Right. But notice that n equal to 1 to infinity, so n is positive. So we have a positive here and a positive here. So we can write like this. That term will be less than, or we can throw in the equal sign too if we want to. First of all of them are positive because n is positive. Now, the reason this one is bigger, because we still have 2, both the 2 on the top, but the denominator here is bigger. Divided by a bigger number result in the smaller quotient. So that one, the quotient is smaller than that one. And then we're going to put, because of that, because all of them are positive. Now we're going to put the summation notation in. If each term is less than, the sum certainly will be less than or equal to as well. N equal to 1 to infinity. Of course, there's nothing wrong with that term is certainly bigger than this. Right. So what we see here is that this term is the P series when P equal to 1/2. And so this one is divergent. So if it is divergent, we cannot do it like this. So this doesn't help. Because if it's less than divergent, it could be convergent, it could be divergent. So this one doesn't help at all. Right. So this solution doesn't work like this. Because if it's less than divergent, it doesn't work. If it is greater than divergent, then that will work. So let's focus on that. So this one, it doesn't help us at all. Let's draw a line here. Now, because less than divergent could be anything, could be convergent, could be convergent. If we have something greater than, then that's great. So what is that greater than? So let's just write that term again. Now, actually what this one is greater than is going with, we need, so this direction doesn't work because that one divergent. What we can say is, how about it is greater than n. Right. So how did that help and why do we come up with that? So let's look at this. If we have 7n to the 1/2 plus 9n to the 1/3 and we compare with n. Remember, if we put all of this together as a polynomial, this one to the first power has the highest power. So this one has the higher power than everything else. So this one is bigger than that as n goes to infinity. This is what we have for sure. Now, if this is bigger than that number, divide by the bigger number will result in the smaller quotient, right? So, divide by the bigger number here, result in the smaller quotient. So this one is smaller than this because here the denominator is smaller denominator, bigger the quotient, right? Then we're going to throw in the summation. And that will work with the summation as well. Now we look at this series again. This time, this one is a P series when P equal to 1. So P series, what happened when P equal to 1? Let's go back up on P series. When P less than or equal to 1, it is divergent. So in this case, that one is divergent. And this series is bigger than a divergent. If it is divergent already, anything bigger than that will be divergent as well. Just going to put that in here. So anything bigger than divergent is divergent. On this one, it doesn't help because less than divergent is inconclusive. But bigger than divergent will be divergent for sure. Right. On this one, we have sine n and cosine n. One thing we know that if we use the comparison test, when n goes to infinity, actually that could be negative. So the direct comparison test here might not work, but don't worry, if it's negative it's even better. I'll explain why in a minute. So first we have sine of n and cosine of n. Actually, if we notice, if we multiply by 2, that is the double angle. Right. So sine n times cosine of n equal to sine of 2n over 2. Right. Regardless of that, if we have sine of anything divided by 2, this surely will be less than 1 divided by 2, so less than 1/2. So we have sine and cosine is less than 1/2. Right. Now, so let's say sine n cosine of n less than 1/2. Now if we divide both sides by 4 to the n power, it is positive, so don't need to reverse the inequality. Actually make it equal to. Of course it's greater than -1 too, but that's all we need, by the way. And then we're going to take the summation. So we have 1/2 or 4 to the n power less than or equal to, sorry. We write right. So what kind of series is this? I mean the 1 over 4 to the n power. Now, if we rewrite this as, still have 1/2 though. If we write the 1 over 4n as 1 over 4 to the n power. So this actually is a geometric series. Geometric series with the ratio of r equal to. So the left hand side is a geometric series. With r equal to 1/4. And we'll go back to geometric series. Geometric series, if the absolute value is less than 1 and this one is 1/4 is less than 1 and greater than -1. So yes, so r is between 1, -1 and 1 to check. So this on the right hand side is convergent because of geometric series with r equal to 1/4, r between -1 and 1. So we have, let's just write this out and it will become very clear when we write out like this: sine n cosine n over 4 to the n, and this one is less than or equal to. This is a convergent series. Then that certainly will be convergent. So this one convergent with a little twist, right? There's a little twist in this problem because sine of n and cosine n, when n goes to infinity, this term could be negative. But if it's negative, it will be even smaller than that. So it is even better if this one is negative. Think about that. The term is just getting smaller and smaller, by the way. The magnitude of that. So if some of the term are negative, it's even better because the sum is get even smaller. I think later on when we go back, we should go back to this when we go to the absolute convergence. Right. So this is the direct comparison test, and we just did, or we did the, sorry, forgot to update the root test. 13, we already did that. Limit comparison test, we got 14 and 15. We go back to this and make a comment about some term being negative. Right, limit comparison test. On the limit comparison test, we should find a function that compare with the limit. So usually when the limit comparison test, all I do is I will take the highest power on the top and the highest power on the bottom. So I'm going to take this term and that term. So let's compare with the series of, again, ignore the a and the 4, we just take the square root of n and n to the 3/2. So will be n to the 1/2 on the top, equivalent to the square root at the bottom, n to the 3/2. So when we do this, subtract the exponent. 1/2 minus 3/2 is minus 1/2. I'm sorry, minus 2/2, which is minus 1. So we have n to the minus 1 will be 1 over n. So we're going to compare with 1 over n. This time we use the limit comparison test. So we're going to take the limit of the ratio of these two series, to sequence, if you will. Right. So we're going to do that. Let's focus here. All right. Right, first, let this be a sub n. So we're going to take the ratio of this. I will write that to the 1/2 though. Remember the ratio, so we have to divide it by 1 over n. So what we did was an over bn. Right, so that term over this term over that term. Rather than write one big fraction, I just write division. Multiply reciprocal. Right. Multiply the n on the top. To the first power, when we multiply, we add the exponent 1/2 plus 1 is 3/2. Right. Now, as n goes to infinity, the highest power term matters, so we're going to have that over that. Only the highest power term matters, and it cancels out. 8 over 4, so it won't be 2. Right. What happens if we have 2? So the ratio says if it is less than infinity, if it's less than the infinity or any finite number, that is, then in that case the conclusion will be the behavior of that sequence of that series is the same as that series. Now let's look at b sub n. If we find the sum of b to the n, now this is the harmonic series or the p series when p equal to 1. Which means divergent. Now, if b sub n, the series b sub n is divergent and the ratio is equal to 2, meaning that there will be divergent. This series is divergent as well. So the behavior of them will be the same if the limit of the ratio is anything finite. So this one divergent. Alternating series. Alternating series is where the sign alternates between negative and positive. So it is convergent if we have two conditions. First, we have this, which means I'm sorry, there's a typo on the formula. I forgot that it have to be -1. Sorry. There should be a -1 here. So let me write that again. So that's bad. Right. Alternating series, meaning that we're going to have the -1 to the n power, or n plus 1, or n minus 1, doesn't matter. And then a sub n. Let's use k. I should update the formula. So we need that is the alternating factor. Right. We can say n go to 1 to infinity. Right. Sorry. It has to be like this. So alternating series is convergent if two things need to happen. First of all, it has to be decreasing. Decreasing meaning that we have to use either k or n. Let's use k. Meaning that this term is less than or equal to the next term. And the second one, the n term has to go to infinity. I'm sorry, has to go to 0 when n goes to infinity. As k goes to infinity, a sub k goes to 0. So we need to have those two. Alright, so let's take a look at this. First, now notice that in the alternating series, we're going to ignore the alternating factor. So we're going to ignore that. We will write as n equal to 1 to infinity, -1 to the n. That is the alternating factor. And this is what we will let equal to a sub n. I mean, this is a sub n. Now this one should be obvious because 1 over 5n cubed plus 1. The bigger the values of n, the smaller the quotient. So this one for sure is decreasing. because the denominator keep getting bigger, the quotient will getting smaller, so that is decreasing, so that's good. Now we take the limit at n goes to infinity of a sub n. Now because when n goes to infinity, that one goes to infinity, a finite number divided by infinity, so this one equal to 0. So that one check as well. Because of that, this one is convergent. Right. So pretty much we just check two things, decreasing and the n term has to go to 0. So rather straightforward. I need to update the formula though. Sorry. It have to be with the negative 1 to the n power. Right. We don't need 18 here, so just do 17. Right. Absolute convergence, conditional, convergent, or divergent. Right. So when we look at this, again, that negative to the n power, so this is alternating series if we want to use it. Okay. Now, if we rewrite this, by the way, if we put the absolute values into it, that's what we do. Actually, let's just do that. We're going to do both, by the way. Let's use the alternating series thing first. If we write that as negative n1 to the n power, then we just have a to the n and 8 n squared plus 5 to the n. Right. Now let's check two things. What happens when n goes to infinity, and is this one decreasing? Right. It will be a lot more complicated. You actually have to solve for it. But if we just do the reasoning here real quick. Let me ask you this. A to the n power, this term is a lot bigger than 5 to the n. Right, so that's the first thing. Second, a to the n is a lot bigger than a n squared. I remember when we do the growth rate, the n squared is, if we take a look at the graph of the n squared, it is just a quadratic, kind of quadratic function. That a to the n squared though. Let's use, so this is a square. Now the a to the n power, that is exponential, so that one go to infinity a lot faster than quadratic. So the top go to infinity a lot faster than that term, a lot faster than this term. Actually they're comparable, but regardless of that, this is not decreasing, so it is divergent. Because we don't have the decreasing sequence here, so that doesn't work. So actually what we do is we use the absolute conversion, so we will slap the absolute values into this. I'm going to put the absolute values so this is just turn to a to the n there should be a lot of options here. We could use limit comparison test or a lot of different things, but what we see here is, remember, let's just write the rate. A sub n is a little bit bigger than 5 to the n power, but either of that is a lot bigger than a to the n square. So those two terms going to be bigger than 8n squared. Quadratic is not going to infinity as fast as exponential function. Right, so what I'm going to do now is just the diversion test, because now if we take the limit of this term when n goes to infinity, remember, because those two terms is a lot bigger than a to the n square, so we just ignore that. The limit equal to a to the n over 5 to the n, and regardless, this is not equal to 0. If the n term does not go to 0, the sum is going to be divergent either way. So this is divergent by the diversion test, and if the absolute value is divergent, so with absolute values that will be divergent. Alternating series, that is also divergent. So it will divergent with absolute values. By the way, absolute divergent is not a thing, so actually this doesn't help as much. What we can say is it is divergent. So this solution doesn't help at all, because we don't have the absolute divergent. Absolute divergent is not a thing. So if we have divergent when we do the absolute values, that doesn't help us at all. So we just stick with the alternating series, which is divergent, because that is not decreasing. And besides, if we take the limit of this term, it does not go to 0. So both criteria, remember, for alternating series we have two criteria. The first one, it has to be decreasing, which is not. The second one, the limit when a sub n when n go to infinity is not equal to 0 either. So we fail on both of them, where we only need to fail one to say that it is divergent. So either one of this, we only need one of this to show that it is divergent. Because when we put the absolute values in it and it turned out to be divergent, we cannot say anything about absolute convergent. Can put absolute values or not, because absolute divergent is not a thing. So that doesn't help when we put absolute values and it is divergent. Right. Number 20, I will rewrite this as just write that again, I don't know, for no reason. Right. Negative power, we can write that like this, and 1 we can say to the n power as well. So I will move both of them inside the power of n. Right. On this one, actually we're going to put the absolute values in and see what happened. What happened if we put absolute values? We just have this. Without the negative. Now, this series is a geometric series. We have two kind of the P series and geometric series. Let's just compare this real quick. The P series is we have something raised to the constant power. So if the power is constant, that's the P series. Right. This one, the power is not constant. So again, let's go to the P series again. We see the P is the power, is a constant, does not change. On this one, the power change with n. So when that is the case, that is the geometric series. And the geometric series with the ratio is equal to 1 over 3, which is between -1 and 1. Which means this is convergent. Now, if it is convergent with absolute values, so we can say 20, this is absolute convergent. Absolute. If it is absolute convergent, it certainly will be convergent as well. We cannot go back the other way. Absolute convergent is convergent, meaning that it is convergent with the absolute values, then it will be convergent without it. Think about this. If we just have all the positive numbers, we have something that is the sum that is convergent. Now if some of the term happen to be negative, let me have some paper. So let's say we just have let's pick a P series when P is equal to 2, for example. So the P series, the power is the constant. This one is convergent because the P series when P equal to 2, it is convergent. Now, if it is convergent, if I just change the sign of this to negative, every other term, we even get a smaller number than this, which is still convergent. So, if it's convergent with the absolute values, it will be convergent without it, meaning absolute convergent will be convergent. And just go back to the previous one, absolute divergent is not a thing, so we never, it's not a term, so we're not going to have that. So if we put absolute values in and we have divergent, nothing can be said about this. But if we put absolute values in, it is convergent, then it is absolute convergent, and it certainly will be convergent as well. Skip this last one. Taylor series or Maclaurin series. This will be similar. The Taylor series, we have the formula here at the end there. I can zoom in. Right, better. Standard 8. So that is, in general, the n term is given by this term here. Sorry. I mean, that is the n term of the Taylor series. Right. All we need to do I'm going to do 22 and 24. By the way, the Taylor series that center 0 is called the Maclaurin series. If they center something else, it's just Taylor series or polynomials. Right, now I'm going to do either one of this. I just pick 22. So usually for this one I'm going to have a table. So we'll have a ruler here. Just make a table. So notice in the formula we have three things: the derivative, the n factorial, and that term. Not sure how many we get here, but we need three terms. So we can choose n equal to 0, and then 1, 2, 3, and that's it. To pop all the 3, so we go up to n equal to 3. One, two, three. Right. The first term is f and derivative. After that, we do f and derivative at the point a. In this case, a is 0. So derivative in general with x, and then derivative with 0. And after that, we're going to divide by n factorial. And after that, multiply by x minus a, in this case 0, to the n power. So we just have x to the n power. Right, so it will be like this. Switch to different colors here. So the function is e to the negative 2x. Just take derivative, negative 2 e to the negative 2x, 4 e to the negative 2x, negative 8 e to the negative 2x. Next we're going to put 0 in for x. So first we have the derivatives, the function and derivative. Then we're going to put the values into x, so 0, 0, 0 here. E to 0 power is 1, so we're going to have 1. Just keep the colors here. 1, negative 2, 4, and negative 8. Next, we divide by n factorial. 1 factorial, 0 factorial is 1. So we have 1 over 0 factorial will be just 1. Negative 2 over 1 factorial, negative 2. 4 over 2 factorial, 2 factorial is 2, 4 over 2 is positive 2. And negative 8 over 3 factorial would be 6. Negative 8 over 6, negative 4 over 3. So we have those numbers. And finally, we take those numbers, multiply x minus 0 to the n power. So first, 1 times x minus 0, just x, n is equal to 0. So that's what we have. The first one is 1. Next, negative 2 times x minus 0 to the first power, negative 2x. And then 2 x minus 0 to the second power for x squared. And then 3, I'm sorry, not 3, negative 4 over 3 x minus 0 to the third power is negative 4 over 3 x cubed. And we add, just combine all of those terms and that's it. We could go higher than this, but we just said the function approximately equal to 1 minus 2x plus 4x squared minus 4 over 3x cubed. Right, so that is the Taylor polynomial, or if we just want a polynomial, that would be it. Again, the function and derivative, evaluate at the point, divide by n factorial, and then multiply by the factor. Right. So that is Maclaurin series and the Taylor series, or the Maclaurin polynomial, if you will, because evaluate at 0. This one is just a plain old Taylor series because we will evaluate at 5. Right, I'm going to make a table on this one as well. We also need 3 terms, up to order 3, meaning we're going to need up to n equal to 3. N equal to 0, 1, 2, and 3. First we have the function take n derivative. Once we do that, we're going to have the n derivative evaluate at this point. After that, whatever the term we have divided by n factorial, and whatever term we have we multiply by x minus that number to the n power. Right. So we have ln of x. Derivative of ln of x is 1 over x, which is x to the negative 1. And derivative is negative x to negative 2, or negative 1 over x squared. Derivative of this is 2x to negative 3, or 2 over x cubed. Right. So we just keep taking derivative, that is this column, function and derivatives, and then we will put 5 in for x. So we have ln of 5, 1 over 5, negative 1 over 5 squared, 25, and 2 over 5 cubed is 125. And then we will divide by n factorial. ln of 5 divided by 0 factorial. 0 factorial is 1. So this is ln of 5. 1 over 5 divided by 1 factorial, which is 1. So just 1/5. Negative 1 over 25 divided by 2 factorial, which is 2. Divided by 2 is multiplied by 1/2. So negative 1 over 50. And 2 over 125 divided by 3 factorial, which is 6. 2 over 125 times 6. 6 and 2 cancel. We have 1 over 125 times 3. Let's say 375. Right. So those are the coefficients. Then now we just multiply the power of x minus the number to the n power. So we have ln of 5 times x minus 5 to the 0 power, or just ln of 5, because 0 power is anything raised to 0 power is 1. So that is just 1. Except for 0 raised to 0 power. Right, 1 over 5 x minus 5 to the first, negative 1 over 50 x minus 5 square, 1 over 375 x minus 5 cubed. Right, just combine all of this. We have the Taylor polynomial degree 3. So that's the third degree polynomial. Next we have the radius of convergence and interval of what we're going to use. Let's look at that one again. What we're going to use in the radius of convergent or interval convergent, we're going to use the ratio test. Oh, by the way, happened to forgot that. Remember, I said that we go back to number 15 when we go to the absolute convergence. Again, let's just talk about this again. If we have convergence with absolute values, then it will be convergent. Without it, absolute convergence will be convergent. So in this case, all we do is we just going to put the absolute values in it. It is still convergent. Absolute convergent will be convergent. So this one, technically, we should put the absolute values in this and say it's all positive and it is convergent. So convergent with the absolute values, it will be convergent. Without it, radius of convergent, we're going to use the ratio test for this kind of problem. Right, the ratio test. So let's take the ratio. By the way, this should be n equal to 1, otherwise it is undefined here. Right, so we take the ratio test. Notice that all of this series now, we have an x now. It's not just the variable, not just the index n. We should have an x in here. Right, so we're going to take the ratio of a of k plus 1 over a of k. So in this case, we take the ratio of a of n plus 1 over a of n. We can write one big fraction, or we can write the fraction and dividing. I'm just use the big fraction in this case. X minus 4 at n plus 1, so we put n plus 1 in for n. N plus 1 cube 9 to n plus 1 over just the term a of n. This is a of n. Right. Multiply reciprocal. There should be something to simplify in here. Multiply reciprocal n cube 9 to the n power x minus 4 to the n plus 1. There are a lot to simplify, but before we do that, I want to rewrite this. X minus 4 to the n plus 1, so we have x minus 4 to the first times x minus 4 to the n plus 1 cube. Cannot do anything with that. 9 to the n plus 1 is 9 times 9 to the n cube 9 to the n x minus 4. There's no plus 1 here, sorry. So just n. Right. We can cancel this. 9 to the n. And that's it. By the way, one more thing though. The ratio test, if you look at that ratio test, it only have to be positive. So we should put the absolute values here. Right. Now if we simplify a lot of things, end up with x minus 4 n cubed over 9 and plus 1 cube. Now notice that everything except the x minus 4, the n cube is positive, 9 is positive, and plus 1 cube is negative. So we don't need the absolute values for those things. So I just write n cube over 9 and plus 1 cube and x minus 4. Right. Now, next we find the limit as n go to infinity. Again, this one, the n has the higher power than 1. So we just have the n cube. So n cube over n cube. Let's see. Because n plus 1, when n goes to infinity, n is a lot bigger than 1. So 1 is just throw away and we just have 9n cubed and x minus 4. Now n and n cancel out, so pretty much this limit is equal to 1 over 9 absolute values of x minus 4, and it is convergent. If it is less than 1, it will be convergent, meaning that x minus 4 will be less than 9, and so 9 is the radius of convergence. Radius of convergence is equal to that number, which is 9. Right. So that is the radius of convergence. Now we find the interval convergence, kind of like that. It's only a little more work. Interval convergence. Right, 26. It might take a little more space, so I try to write extremely small here. First we take the ratio of the next term over this term. This time I use the division instead. A sub n plus 1, so we have x minus 1 to the n plus 1 over 5 n plus 1 plus 4 divided by a sub n right, because we kind of run out of space, so I skip a few steps. First, that to the n power is going to be x minus 1 to the first, and x minus 1 to the n power, and 5 times n plus 1 plus 4 will be 5n, 5 plus 4, so plus 9, multiply reciprocal, 5n plus 4, x minus 1 to the n power. And again, I forgot, we have to have the positive to use the ratio, so we throw in the absolute values. Right, so we have limit n goes to infinity. Right, that cancel out, and we just have this. Again, the 5n plus 4 is positive, 5n plus 9 is positive. Bring that outside of the absolute values. 5n plus 4, 5n plus 9, absolute values of x minus 1. Now, as n goes to infinity, the highest power terms matters. Only the highest power term matters. So we just have 5n the higher power and 5n the higher power, and this is pretty much cancel out. We just have absolute values of x minus 1. Now this is convergent if it is less than 1, so we say convergent if x minus 1 less than 1, absolute values of x minus 1 less than 1. If we're going to solve for it, we have x minus 1 is going to be between the negative and the positive, which means x is between 2 and 0. Right, so it is convergent if x is between 0 and 2. Right, we're not done. Because if this is equal to 1, notice that if the ratio equal to 1, it will be inconclusive. So we have to check differently when it equal to 1. Meaning that what happened at the end point here. So at x equal to 0, we're going to have the series of 0 minus 1 to the n power of 5n plus 4. Right, this is of course with the negative, so that is alternating series, and as mentioned before, we need a lot of space in this one. I will write negative 1 here, and then we just say 1 over 5n plus 4. So this is going to be a sub n here. Alright, alternating series. Again, I forgot the negative 1. I forgot the negative 1 here. I'll fix that later. Right, so this is a sub n or a sub k. Two things. Let's say n, because we have n here. It is decreasing because the bottom number goes to infinity. The bigger the denominator, the smaller the quotient. Essentially, it's equal to 0. I mean, it gets smaller and smaller, and it gets to 0 as well. So we say limit of that term go to 0 as well. So we have two things, decreasing, which is good, limit go to 0, which is good. So this is convergent by alternating series. So equal 0 here is good. Next, what happened at the other endpoint of 2? So if we have 2 here, we have n equal to 0, 2 minus 1 to the n power 5n plus 4. So we just have n equal to 0, right. Now, kind of run out of space here. But if we compare this, actually I'm going to use the limit comparison test, and we compare with 1 over n. So compare with 1 over n. You take the ratio of these two, it is a constant, it's a finite number. So both of them converges or both of them diverges. This one, the harmonic series, diverges. So is this one. So it's divergent. So we only have equal to 0 but not equal to 2. I'll let you do number 27. Right, the last part we have the power series. In general, I'll find a function that represents the power series. Actually, this is rather simple because what we have here is just a geometric series. So we just have x minus 6 to the 0, and then so this is a geometric series. Where the first term is x minus 6 to the 0 power, which is 1. The ratio is x minus 6 itself. So assuming that r is between -1 and 1, so let's say assume x minus 6 is between -1 and 1, or absolute value of x minus 6 is less than 1, which is equivalent to x minus 6 between 1 and -1. If that is the case, then this is the geometric series, and the geometric series, we have the sum is that. So a over 1 minus r, 1 over 1 minus x minus 6, 1 over 7 minus x. Right. So just like that. We do the same thing here. This is a geometric series as well. The first term is when n equal to 0, which is x plus 3 to 7 to the 0 power, which is 1. The common ratio is x plus 3 to 7. And assuming that it is between -1 and 1, then we can say the series equal to a over 1 minus r, a over 1 minus x plus 3 to the 7. Simplify this, multiplied by 7, top and bottom. 7 over 7 minus 7, x plus 3. So 7 minus 21. 7 minus 21 is minus 14. Oh, sorry. When we multiply like that, that 7 cancel out. Yeah, only the 7 here. And it looks strange. 7 on the top, 7 minus x minus 3, so 7 over 4 minus x. Right, so because it is a geometric series, so just the sum is equal to the first term divided by 1 minus r, and that's what we have. So same thing here. So this is, of course, the formula is right there, but if we want to write that, this is a geometric series. The first term is equal to 1, or a is equal to 1, and r is equal to 3x. So if we're going to write that out, it's going to be 3x to the 0 power, 3x to the first, 3x square, and so on. In general, it will be k equal to 0 to the infinity, 3x to the k. Right. So that's what we have. So pretty much that cover everything on chapter 9 and chapter 10. I hope you found this video helpful. Thank you for watching.